Okay. Yeah, I saw some of the posts from from the South America region.
Okay, we're going to get started. Okay, one more time, we're going to get started. Hello?
Good morning.
I have a sore throat and a cold, so my apologies for that. You'll see me with a mask on. This is what I look like without a mask. Maybe the mask is a better deal for you all. So my name's Al McGovern. On behalf of Jeff Jansen, I think most of you know Jeff, and Akanksha Garg, who cannot be here today, we want to welcome you, good morning, and welcome you to this Mike Sepe Symposium, where we'll honor Mike by having 7 technical papers given by his friends, and those friends have been asked to include some of their personal remembrances about Mike in their talk. But we want the talks to be technical in nature. You come for technical content to Antec, and I can assure you these are technical papers for sure. So 4 presentations, some things you should know. 4 presentations will be 1 hour long. That's a little unusual for Antec. So that means if you have a presentation, if you built your agenda for the day and you thought you had a 30-minute talk and it's an hour and you need to leave to get to the next talk, please do so. Please do so quietly if you can. The speakers know that that could happen, okay? And conversely, please feel free to come back in for an hour presentation. If you're gone for the first half, you can come in again quietly and join the conversation here. Breaks are at 9:30, 11:30 to 1:30 for the awards luncheon, and there'll be a 3:30 break in the afternoon. So we do coordinate with those with the rest of Antec. In the back there on the table, there are 2 posters, they're similar posters, for you to write your sentiment about Mike. If you have personal remembrance or anything you want to say, I'm going to send those to Audrey, Mike's wife, and Christina, his daughters. They'll get those at the end of the event here, along with some other things we're gathering as well. Let's see. Sorry again for the mask. I will cough once in a while. Really sorry about that. Last thing, in front of you are these little cards. There will not be a test. There's 2 QR codes. You scan them. You can contribute on the code next to Mike. You can contribute to his scholarship. As you may know, the SP Foundation funded a scholarship in Mike's honor. While it is fully funded, there can always be more put in. That just means more gets paid out to the scholarship recipient. And the other one is for Glenn Beal. Hopefully you all know Glenn. If not, you should look him up. One of the icons of our industry. So this will be announced at lunch today. You're hearing it first here, that there is a Glenn and Patsy Beal scholarship, honored service member scholarship. So you could be among the first to contribute. So with that, I'm going to introduce Jeff Jansen, our first speaker. So forgive me, I'm going to read this because I don't know Jeff that well. Jeffrey A. Jansen is the engineering manager and a partner at the Madison Group, an independent plastics engineering and consulting firm. And by the way, really, really, really good friend to mine. Jeff is a proven plastic professional with more than 30 years of experience solving problems and addressing opportunities related to polymeric materials, and has performed over 5,000 investigations. Investigations, Jeff. He specialized in failure analysis, material identification and selection, as well as compatibility, aging, I can talk about aging, and lifetime prediction studies for thermoplastic materials. Jeff enjoys sharing his plastics knowledge and is a regular presenter on the SPE webinar series, covering a wide range of topics related to plastics failure, material performance testing, and polymer technology. Jeff is a graduate of Carroll College and the Milwaukee School of Engineering, MSOE. Jeff was elected as a fellow of the Society by the Society of Plastics Engineers. I give you Jeff Jansen. Lost it. There it is. You all set?
It's my pleasure to be here to honor Mike. See if we can make it through this first part. So when we contacted Audrey, that's Mike's wife, to see if she would like to say something. She wrote this letter, so we're going to see if we can get through this. So the title of the letter, she did this very, very well. The title of the letter is The Plastics Industry's Gift to Mike. I think it's the opposite way, but and she prefaced it by saying, the real meeting between people happens over time as they remember each other and the experiences they share. In August of 1975, a young man stood next to a 375 Cincinnati injection molding machine. This was the beginning. His first day in a nearly 50-year journey deep into the world of plastics. He stood there emanating curiosity, enthusiasm, innocence, and a sense of wisdom, yet unleashed. This was my first glimpse of Mike. I remember every detail of it as if it happened yesterday. Although it was only the beginning, the entirety of what was to unfold seemed somehow present in that moment. I was privileged to become his life partner and a witness to his discovery and fulfillment of his dreams and passions. This path he chose, a path that included an intersection not only with the mechanics and science of the plastics industries, but also, most importantly, the intersection with the people who were its innovators, contributors, and the driving forces for its advancement. Whether it was while teaching or consulting or problem solving, the highlight for Mike was always connecting with you, his colleagues, his customers, his mentors, all of whom he developed deep friendships with. When Mike and I first met and began our relationship, he would leave me handwritten notes on my desk for me to find. I still have all those notes, and in rereading them shortly after his death, one in particular stands out. Although at the time it was meant for me, it reflects how his life and what he most valued. It's a quote from C.S. Eliot. When you and I met, the meeting was over very shortly. It was nothing. Now it is growing something as we remember it. What will it be when I remember it as I lay down to die? What it makes in me all my days till then. That is the real meeting. Mike's life was a collection of cherished moments woven together, forming his life's journey. All of you who shared yourselves with him provided him with everlasting kinship that brought him great joy. He did not get to say goodbye to any of you. But on his behalf, I assure you that you were all an integral part of who he was and an integral part of what can be carried forward. This is the true gift he received from you. For you are the very heart and soul of the plastics industry. For this gift, both Michael and I are forever grateful. Audrey Sepe. Typically, I like going first to present, but
So you got
Okay.
behind you, and here's your
thanks.
thingy right there.
Yep, thanks. So, what we're going to talk about today is you've had a failure, now what? Determining the how and why of plastic failure. Now it's not.
The right arrow.
Oh, the right arrow, yes, thanks.
You got it.
So, this is the picture that we remember of Mike, but if you go back, this is the picture of how I first met Mike. So, or about that time. Mike did an article series it started for Injection Molding Magazine. It developed from there. And this was the cartoon that they used. And I thought it was very, very appropriate. I mean, looks a little bit like Mike. And if anybody could get out of the plastics material everything it had inside, it was Mike. He truly was the materials analyst. So, a little bit about the first time that I met Mike. I met Mike in 1996. So, just about the time I was really starting my plastics journey. I had just gone to a company called Stork Technomet in New Berlin, Wisconsin, metallurgical firm that was starting their plastics laboratory. And we wanted to get that off the ground. So the person that was charged with sales and expansion of that said, you know, there's a molder over in Nashota called Dicton and Mosh. There's a guy there named Mike Sepe. We should go there. we should be able to sell him plastics testing and consulting. I didn't know Mike at that point, so I said, yeah, why don't we go visit Mike? And so we went to Mike, he got an appointment with Mike. I got to go through my little spiel about how we're going to be able to help him with plastics testing. It was obvious from the very beginning that Mike was not only gracious and let me talk, but that Mike had knowledge that was both deep and broad. And so by the end of that meeting, Mike was doing our melt flow testing and our DSC testing. And so, that's where things kind of started between Mike and I. So over the course of our time that I knew Mike, Mike started out as a supplier, as one of our laboratory partners. We ended up eventually doing some testing for Mike, some FTIR, some fractography. We ended up being a supplier for Mike. Over that time period, Mike was a teacher for me. Mike was a mentor, and Mike was a friend. I was lucky enough to, my wife and I took a trip out to the Grand Canyon. If you know Mike, he was very passionate about the canyon. And so we went to the canyon. We didn't hike rim to rim like Mike does. We actually took the mules down, which Mike said he'd never do. But while we were in Sedona, we were able to go out to dinner with Mike and his wife, Audrey, and that was a cherished memory for us. So I lugged this all the way here from home. I took up a whole suitcase. So this is where my plastics knowledge started, okay? It's with this collection of Mike's articles. I religiously copied them, put them in this binder, reviewed them. This is the first 100. There's another 2 binders that are just like this back at home. And so if anybody wants to look at them, there they are. I mean, that's where, if you were here last year for Glenn said that he started to collect things and that's how he gained his knowledge. This is how I gained my knowledge, was by reading Mike's articles. He couldn't help but interact with Mike on any level and absorb some of the knowledge. So with that, let's go ahead and get started. But before we get started, this is a graph right out of one of Mike's presentations, okay? And I'd like to talk about this, but I'm not gonna. What I'm gonna tell you is that if you've ever heard Mike talk, you know that he put a slide on the board. He'd talk about that slide for 10 minutes. There's no words on that slide. Mike would just dive into it, rip it all apart, and he'd talk about that slide for 10 minutes. If you've ever seen me talk, or as you're gonna see over the next half an hour or so, I talk in 2 slides a minute, okay? We have very, very different styles on how we present things. But, you know, Mike, he could put that up there and he could talk longer than 10 minutes about that slide. And I guarantee you would get a lot of information out of that. So with that, let's jump into my presentation. So, failure. How do we define failure? There's a lot of different ways that we can define failure, but I'm simply gonna say that it's something not performing the way it was intended. That's a nice simple definition that we can get onto failure, okay? And there's a lot of different categories. Lots of times we jump and we think about fracture when we think about failure. But failure can take many forms. It can be deformation or distortion. Aesthetic alteration, your nice, bright, white part turning to straw color that the consumer doesn't appreciate, okay? Molecular degradation, wear, fracture, as I said, or modification of the formulation over time out in the environment. All of those things can be failures, and there's more. I want to get our mindset right. As we go through today, we're going to focus mainly on fracture. But a lot of the concepts I'm going to talk about apply to anything. Again, failure defined as something not performing the way it was intended. So when we have a failure, regardless of the type, there are many different reactions. And I've been working in industry first before I got my consulting, so I've seen many of these from both sides. First of all, you can deny the existence of the failure. Question the motives of those identifying the failure. You know, that's Bob. He's just bringing things up because he wants to talk. It's not really a problem. Don't worry about it, okay? Or you can do nothing. You know, we see this once in a while. We don't need to worry about it. This problem will go away in a couple of weeks. It always does. Just don't worry about it. Or we can act on theories. We can take the shotgun approach. So again, when I was at a company called Cooper Power Systems, we had an engineering manager, and he'd go to the board when we had a problem. Usually we had a problem. It was Friday at 3:30 in the afternoon, but we had a problem. You'd get together with engineering, design engineering, manufacturing engineering would be there. Purchasing would be there, quality would be there, the lab would be there. Frank would go to the board and run the meetings. And he'd be there with his shirt on, talk to the big guy, writing things down on the board. And he wanted people to give suggestions. Now, if he liked your suggestion, he'd write it on the board. If he didn't, he wouldn't write it on the board. Then he'd send people with these 10 things, and he'd send them out in different directions. Go work on these. Well, that takes a lot of effort, but you haven't really pointed yourself in a direction yet. Again, that's what I mean by acting on these theories. Or we can take a systematic problem-solving approach, which over the years I found tends to be the most efficient and effective way to solve problems. So we're going to start with this Mike Sepe example. This came right out of one of these Material Analyst articles that Mike had put together. And it's a great illustration. By this time in this series, Mike and I, we're talking pretty regularly. And so I appreciated this example. So here he was working on a problem. He had some dark gray polycarbonate parts that exhibited some splay, some gray streaks. There's a lot of details about the mold. I won't bother to go through those, but he collected that, kind of background information. And so the way that they chose to approach this, not with Mike, but the way that the company chose to approach this before they got Mike involved, was a week of troubleshooting at the press. Okay, if you mold your own parts and you're having problems with parts, a common example or common output is to go to the press and try and fix it at the press, right? And so after about a week at the press, they got nowhere. So they sent some samples to Mike. They sent a sealed jar of some raw material that came right out of the dryer, because what did they suspect? The material was not being dried properly. They sent a larger sample of raw materials for some melt flow rate testing, and they sent a very large part showing these cosmetic defects. Well, some testing showed that the material from the dryer was dry. So it was dry. It wasn't a drying problem. Melt flow rate testing showed that the material was being significantly degraded during that injection molding process. Okay, but not because it wasn't dry. Impact testing showed that normally polycarbonate, a very ductile material, was behaving in a brittle manner, which is consistent with that molecular degradation. They did one more test, further a melt stability test, and that was performed on some various samples that were colored and natural. And what they found was that the dark gray material results indicated that material lacked the thermal stability for the injection molding process. Okay, it was supposed to have some additives in there. Again, once all that testing was done, and it wasn't a whole lot of testing, it was very practical testing. That's one thing about Mike. Mike didn't like jumping into a whole lot of testing. He had a focus. Let's do the right tests, and let's get them done, and let's see what that data tells us. Okay? So, once that testing was done, it was traced back to a stabilizer package that was not properly incorporated into the resin. And so the formulation wasn't proper. It couldn't survive the injection molding process. Remember that these are big parts, okay? And so it could not survive that injection molding process. The most common objection to doing failure analysis that I hear, and in my conversations with Mike, he got the same thing. I don't have the time to do a formal failure analysis, and I don't have the money to do that. Okay, well, what was done in 2 days in the lab for, at the time, under $2,000, okay, that's what getting the right answer cost. What did it cost to not do the testing? Well, again, they spent a lot of time at the machine. If you put in some factors, $42,000, they spent 10 hours a day, 2 weeks doing that. So you had some labor costs. You also had spoiled material. You had direct expenses. The total that was spent was approximately $125,000 to not get the right answer. This is a great example. Again, two days, $2,000, or 2 weeks and $125,000, and you don't yet have the right answer. Okay? I contend that the most efficient and effective way to get to a problem, to get to the root cause of the problem, is through testing. Allow the science to direct the investigation. Rear Admiral Grace Hopper once said that one accurate measurement is worth 1,000 expert opinions. And that's true, because we all have opinions, right? And I'm not saying that we should put those on the back shelf. Our experience, our collective experience, our knowledge is very important, okay? But we need to let the science direct the investigation. So what is a failure analysis? Well, it's the process of collecting and analyzing a series of data to identify the cause of the failure, often with the goal of determining corrective action That's, I think, the most important thing. Or liability. Again, if you work with Mike, Mike had no time for working with attorneys to do liability. He hated it. He's done it a couple of times, and he hated it because nobody was interested in finding the root cause of the problem, which is what Mike cared about. That was the joy that he took in his evaluations, was getting to these corrective actions. He didn't care about liability. Okay, you made a mistake, let's fix it. That's what he cared about. So, in a failure analysis, what are the key characteristics? Well, it's a logical and systematic approach, analytical observation and testing, sound engineering practices. Okay? Pretty straightforward. The goal of that failure analysis is to identify the mechanism. That's the how. Okay? The mechanism. And the cause, which is the why. That's what we're after. How and why did this failure occur? Okay? Why is a failure analysis so important then? Well, we hope to certainly solve the current problem with efficient use of time and materials, right? That's what we showed in Mike's example. Efficiently, effectively identify the problem. Generally, problems don't solve themselves. You can't really ignore it. Things usually get worse over time. Okay? We also hope to identify through the failure analysis ways to improve our current and future parts. Okay? We hope to advance our knowledge related to design, production methods, installation techniques, and testing methods. And I think the last one is the most important, the testing methods. And I'm not talking about QC testing to see if it's in spec and things like that. I'm talking about testing methods that we could use to prevent failure occurring during product development. If our product failed through environmental stress cracking, combination of stress and chemicals, did we do chemical compatibility testing? Should we have? Did we do the right chemicals? If it failed through fatigue, did we evaluate this material or the product for fatigue resistance? Again, that's where we can learn a lot. We take our failure analysis and we turn it into knowledge. Let's admit it, nobody likes having a failure. So let's make the most of it. Let's get the most out of it that we can. So through that failure analysis, we're looking for some things, some indicators. What was observed that indicated we had a failure? What are the consequences? This is the ultimate problem that we're hoping to avoid or to solve. Mechanism, again, the how and the causes. What was determined to be the cause? And most of the time for plastics, this is going to be plural. Most of the time, 2 or 3 things are coming together to cause failure to occur. And that's what we're going to address, the causes, in our corrective action. This is good to find out. This is most important to find out, the cause. So let's look at that process. So we're going to collect background information. I like to say that conducting a failure analysis is like putting a jigsaw puzzle together, okay? The background information, all of the things we need to collect, that's the border and the corner pieces of that jigsaw puzzle. They provide the context in which we're going to interpret all of the data, okay? Without that, it becomes very difficult for us to interpret the data. So we need to collect information. Again, just a collection or just an example of some questions. General questions, questions related to design, materials, processing, questions related to installation, and finally, service. What was the environment like? Okay? All of these questions, and I'm not saying because it's a box that you need to do that before you go to the next step. Oftentimes, getting answers to these questions can take days or weeks in many cases, particularly if we're working with somebody remote or offshore, okay? But we need to start to ask these questions up front, okay? So let's start to get that information going. What do we want to understand? What do we want to know about the failure, okay? Next, then, we're going to get to the macroscopic examination. This allows us to use the 2 most important tools we have for failure analysis. It's our eyes and our brain, okay? At this point, and macroscopic, I'm talking about probably 10x, 20x or less, okay? Unaided, with maybe some low magnification also, okay? Look at the parts. Too often, and I know I've been guilty of it, you want to get to that cool stuff, right? Let's generate some graphs, let's generate some charts, okay? But let's look at the parts. Let's stand back. Let's not hone in at 1000x. Let's look at them and see what we see. Do all the parts fail in the same location? Are there obvious signs of damage or abuse? Is there discoloration? A lot of different things we can observe from a macroscopic examination. And by the way, this is our last chance to do things non-destructively. After this, we're going to start to cut that part up. And if you don't understand that part, you can cut through key features. And again, I admit it, I've been guilty of that. Been in a rush with my client, trying to get to answers, rush to that step. Before I know it, I've cut right through the origin of the crack. And that, you can't go back from that. So, again, avoid that. You also take a lot of pictures at this step in case, again, you've cut the part up, you need to then be able to recreate things from those pictures. From here, we're going to select our samples. And by that I mean, what are we going to do? How many are we going to look at? What testing are we going to do on various samples? Okay, so that's where we're going next. Some of those samples are going to go to microscopic examination. And by that I mean magnifications greater than 10 or 20x. Okay, we're going to start to really hone in on things. Okay, we're going to then do material testing, composition, molecular structure, physical properties. And again, I show these in parallel, I show them consecutively. You can certainly do them in parallel. It doesn't really matter. It depends on what you want to do. I like to do all the visual stuff first because sometimes I'll get I'll see some observations that kind of change the path for some of the analytical testing. But again, if you're in a rush, you can certainly do that consecutively. So this is what we're going to talk about when we talk about testing, which forms kind of the bulk of the rest of the presentation. So again, as we said, our goal for the failure analysis is to identify how and why the part failed. Okay? Visual techniques tend to give us most information about the mechanisms, the how. Analytical techniques tend to give us most information about the cause or the why. Again, there's certainly overlap. I don't want to make that exclusive. But that's how things tend to go. Again, through examining the part, you tend to find out how the part failed. And with those analytical techniques, you tend to get a little bit more information about why. The examination part, that's called fractography. It's a systematic study of fracture surfaces, fractured parts. Okay, it's looking at that part. You're going to look at it across a wide range of magnification. So that includes our unaided visual examination, and it includes low power stereomicroscopic examination. It includes taking the part into the scanning electron microscope and going up to whatever magnification you need in order to get your answer. Okay? So again, a variety of different tools that we can use through that fractographic examination. What do we hope to identify through that fractographic examination? Well, we want to understand the location of crack initiation. Where did this crack start on our fracture, on our crack? We hope to identify the mechanism of crack initiation. How did it start? Was it impact? Was it fatigue? How did this fracture start? And then we hope to identify the direction of crack propagation. How did the crack move? Where did it propagate? Also, not always the same as the mechanism of crack initiation, the mechanism of crack extension. For example, you have an automotive part. It gets impacted. A small crack starts, but it stops. It doesn't go catastrophic. But now the vehicle moves down the road and is subject to vibration. So that impact fracture now propagates through fatigue. That's just one example. Okay, so again, don't jump to and think that one mechanism of failure needs to be identified. No, you're looking for multiple mechanisms along the way. We're looking for damage. We're looking for the nature of stresses. So are they compressive? Are they flexural? Are they tension? What are the direction of those stresses? We're looking for manufacturing defects. We're looking for design issues, sharp corners, things like that. All of that comes out of our fractographic examination. This is a key part of a failure analysis. This is where, I will tell you that this is where Mike and I intersected a lot. Over the years, I've done a lot of fractographic examination for Mike, and we would have long conversations about what that meant and how it went. It was one of the times that I felt like I actually got to work with Mike, and I felt on an equal par, and that maybe I actually got to bestow some knowledge onto Mike. So again, what we're looking for are the features that are present on that fracture. So again, thinking simplistically, cracking is a response to stress. It's a stress relief mechanism. Our part is under stress, it doesn't want to be under stress, so it cracks to relieve that stress. We can have a ductile fracture, which is a bulk molecular response that occurs through yielding. So a macromolecular rearrangement followed ultimately by disentanglement, because that's how plastic parts break. Those molecules disentangle. We don't break the covalent bonds that hold those chains together. It's all about disentanglement. Or we can have a brittle fracture, where we skip the yielding. For one reason or another related to the mechanism, we skip the yielding and we go right to disentanglement. Okay? So those are the two basic types of failure that we can see. Again, response to stress that occurs over a given time period. That can be very, very quickly, like impact, or it could be months or years, like a creep rupture failure. Okay? Again, stress over time that affects our part. My approach when I'm going into fractography, this is my approach. I want to understand, do I have a fast failure or a slow failure? Are we talking about something that happened relatively quickly, very quickly, like impact, over a moderate period of time, maybe like you would see during a tensile test, or something that happened slowly? And by slowly, generally I mean days, months, years. Okay? And then I also want to then look at ductile versus brittle, both on a macro and a micro scale. Okay? Because if I put things into these boxes, like I have a fast brittle fracture, well, that leans me towards an impact failure. If I've got a ductile fast failure, that's more like a straight overload failure. If I've got a brittle slow failure, again, then I may be talking about something like creep or fatigue or environmental stress cracking. So again, put things into the boxes helps you to identify the fracture mechanism, in addition to certainly the features we're going to see. So what do I mean by ductile and brittle? Well, this is a pipe, and that we did some burst testing on, and that, from a macro perspective, is a ductile failure. Those two fracture surfaces don't go back together. They're offset. There's stress whitening. There's yielding. That, on a macro perspective, is going to be ductile. This pipe was also burst tested, but they're different materials, obviously. That is a brittle fracture. You could literally put those pieces back together. Now, you'd never do that, right? You destroy your fracture surface. It's intuitive. Sometimes I sit there with clients, they'll take those two fracture surfaces, hey, they go together. But when you do that, you smear some features, you can destroy the fracture. So again, but that, from a macro perspective, is what brittle looks like. From a micro perspective, when we're at higher magnification, the stretched fibrils we see in the upper image, that is ductility. And in the lower, we have a very planar, very flat fracture surface. That typically represents a more brittle fracture. Again, we could talk about fractography for a full day and still not get through everything. But that's kind of what I mean by macro and micro ductility or brittle fracture. So through our fractographic examination, we're going to read the features that we see on the fracture surface like a roadmap. They're going to guide us from our origin to where that crack propagated. And they're going to tell the story for us, again, if we know how to read it, if we know how to interpret it. So we're going to look for features, and this is just a small number of features that we're looking for. Again, these are the kind of things that we're looking for on the fracture surface that guide us, that tell us about that fracture, where it started, where it went, the mechanism of the failure, okay? And so again, we have a lot of different mechanisms that plastics fail under. There are a variety of them. In fact, when we look at things, these are, in a study or in a survey that I conducted, these were the 5 largest plastics failure mechanisms. The largest is environmental stress cracking, that combination of chemical and tensile stress. Then creep is probably number 2, just behind that. Fatigue, molecular degradation, and then impact and overload kind of lumped together as kind of shorter term failure mechanisms. This is what the survey said. In my experience, and I've conducted a lot of failure investigations, thousands of them, I would say that this is right on the money. Nearly 1/3 of the parts that fail that are plastic fail through environmental stress cracking. Creep's not far behind that. I typically don't see quite as much fatigue, but again, but molecular degradation, short-term overload, everybody thinks, all my clients automatically default to overload. Well, somebody overloaded this part. Somebody did something to it, they applied too much stress. Actually, overload is very, very rare. Overload itself, if we separate those two, overload's probably under 5%. Rarely is overload an issue, okay? So, again, the big failure mechanisms. This is what we hope to identify through that fractographic examination. The other thing we want to identify is what the form of the stress is on the part, okay? Is it straight tension? Is it shear? Is it torsion? Is it bending? What kind of stresses cause that? Because if we can identify what kind of stresses, that gives us more information about how to solve this problem, right? So we get a lot of information out of that fractography. Like I said, we read that like a roadmap, okay? So again, this is our stereo microscopic shot, this is our SEM, and the two certainly complement each other. People think that, you know, it's one or the other, or, you know, they don't necessarily. You need to look at things both ways, okay? And we identify that our origin is down here, and our fracture moves in that direction. We have an origin zone, we have a mid-fracture zone, and we have a final fracture zone. And they all tell us information about how that part failed. Again, key information about that, and again, we need to understand how if we're going to try and fix this problem. Understanding that it's important to recognize that different plastic materials will exhibit different features under the same failure mechanism. So what in let's say polyacetal, what appears to be ductile in polyacetal, if we saw those same features in polyethylene, that would be a brittle fracture. We need to understand that one size doesn't fit all for these plastic materials for the fractography. So again, it is a daunting task, and it does take experience, it takes knowledge, okay? And so you have to kind of step into it. The best way to get that knowledge is to break your own parts intentionally, break your own samples, and then study them. So understand what overload looks like, understand what impact looks like. Break some parts through environmental stress cracking. Again, start to understand for the materials that you use, what does that look like? Mike was a huge proponent. Now, he did it for analytical equipment. What he would say about an analytical equipment, if you bring a piece of analytical equipment on board, you shouldn't try and sell that testing for 6 months. You should play with that equipment. You should understand how that equipment works. You should understand the ins and outs of it. Now, that's not always practical, I can tell you that. I mean, you brought on a big capital piece of equipment. There's a lot of pressure to start to sell that test. But again, the importance is you need to understand what that test can tell you and what it can't tell you. And the same is true for fractography, okay? Break your own parts. Understand as much as you can what the materials you work with routinely look like under various failure conditions. With that, we're going to talk about some of the analytical testing that's commonly used in a failure analysis. Probably my go-to test is going to be Fourier transform infrared spectroscopy, or FTIR. Microanalytical technique that's used principally for the qualitative analysis of materials. Helps to tell us what that material is. What are the, you know, what material are we looking for? Are we looking for the right material or not? So an FTIR spectrum is this, where we have absorbance on one axis and we have wave numbers or a measurement of frequency on the other axis, and we're looking at where that spectrum spikes up and where it has baseline. Through that, we can identify the covalent bonds that make up that material. We can do that manually. It's not how things are commonly done. Most of the time, we're going to do some library searching in addition to understanding the material, okay? And what bonds might make up a material, and we're going to verify that we have the right material. Or maybe our material is contaminated, or maybe it's been degraded, okay? Those are the kind of things that we're going to look for. These are the things that we're going to do with FTIR as they apply specifically to failure analysis. Again, identify our failed part. We're supposed to be making this out of polycarbonate. But wow, this is SAN. Okay, the wrong material was used for this resin, okay, or for this part, okay? Qualitative assessment of polymer, copolymers, and blends. So again, if we have a polypropylene copolymer, we can compare A to B to say, yeah, they look like they're the same relative ratio of ethylene to propylene, okay? Or with ABS, again, the same relative ratios of acrylonitrile, butadiene to styrene. We're not going to be able to absolutely determine those percentages, but we're going to be able to compare our known good sample to our failed sample, okay? That's another thing, is we want to have analytical data on known good parts, okay? That may seem like a waste of time. Why would I analyze my good parts? Well, now you know what good parts should look like. So all the analytical testing I'm going to show you, we should have that data for good parts, okay? Or at least have retained good parts so that now we can then comparatively analyze them. Again, so that's what we're looking at. Identification and verification of formulation ingredients. Again, we're talking about major ingredients, not 100 part per million antioxidant, but things like an impact modifier, a filler material, plasticizer, the polymer, of course, are major ingredients. We're going to look for contaminants. Is this material contaminated? Do we see obvious signs of that? We're going to look for degradation. Has the material undergone oxidation or hydrolysis? We're going to look for that. Identification of chemical agents that contacted our part. Remember, environmental stress cracking, our #1 mechanism of plastic part failure. Do we see chemicals on the fracture surface? This would be a great way to look for them. Another test, again, I'm giving you an overview on these. We could spend a full day on each one of these different tests. Another one that's very helpful is energy dispersive X-ray spectroscopy, or EDS. It's another spectroscopic technique, usually done in conjunction with the scanning electron microscope. It allows us to identify what elements are present. FTIR identifies covalent bonds. EDS identifies what elements are present. They go hand in hand, they complement each other very, very nicely. FTIR focused on organic materials. EDS can tell us a lot about inorganic materials. So we get this profile of what elements are present, and then a semi-quantitative picture of of their concentration. So in terms of a failure analysis, we can identify contaminants or inclusions within the failed part. Again, this is done in the SEM, so if we have a small inclusion that we can't maybe analyze by FTIR, we can at least get some information perhaps by EDS. We help to look for qualitative or semi-quantitative analysis of unique heteroatoms. So again, for example, we can identify perhaps if a material has bromine or chlorine, which may suggest that it's got a halogenated flame retardant in it. Or we can look for copper, if this is supposed to be a copper-based stabilizer. We can see, is it there or is it not there? And relatively speaking, is it in the right approximate level? Elemental profile of additives, that kind of goes hand in hand with what I just talked about. Characterization of inorganic fillers. Okay, is this material filled with calcium carbonate? Or is it filled with talc? What's our filler system? Okay, EDS can provide great information in that direction. Differential scanning calorimetry, or DSC, is a thermal analysis technique which measures temperatures and heat flows associated with transitions that the material undergoes. Okay, so again, we're looking for endothermic or exothermic transitions, processes that they undergo, or changes in heat capacity in the material. And that's a typical thermogram that we see, where we see heat flow versus temperature. And we're able to evaluate that graph for a variety of things. We're looking to identify the material. So, for example, FTIR, great job, I talked about that. But you can't differentiate nylon 6 from nylon 6,6 or polyacetal homopolymer from copolymer. DSC can do that because those melting points are different. Again, these tests go together. Again, back to our jigsaw puzzle. You're getting various pieces of the puzzle, putting them together, okay? Material condition, looking for degradation, contamination, oxidative stability of the material. Material properties like crystallinity, very important. Has this material been properly molded? Has it been crystallized properly? Looking for thermal history, heat of reaction if we've got a thermoset material. A lot of different things that brings to the table. Thermogravimetric analysis, another thermal analysis technique, this time that measures weight as a function of temperature instead of heat flow like it does with DSC. So with this, we're able to get a quantitative picture of the material, okay? FTIR, DSC, organic materials, mostly qualitative, but TGA is quantitative. It tells us what the various constituents are by their weight loss profile. So for this nylon 6,6, we've got volatiles, which are likely principally present as water. We've got our polymer. We've got weight loss in air, which is probably the carbon black pigment. And then we've got our residue, which is our filler material. Okay? And so we were able to get a good picture of what quantitatively that material looks like. In terms of a failure analysis, we're going to be able to identify polymers, plasticizers, fillers, carbon black and mineral fillers and modifiers. Identify whether a material's undergone molecular degradation, or at least it can be an indication of that. And help to assess thermal stability of the material. Again, another key technique. Molecular weight. This is, again, very, very important. In fact, if you look at Mike's first article in here, it's all about brittle polycarbonate. and he talks about melt flow rate testing as a measurement of molecular weight. And again, molecular weight gives us various options of different test techniques. Gel permeation chromatography, which gives us the full molecular weight distribution profile. Or intrinsic viscosity or melt flow rate, which give us an indication of the average molecular weight of the material. Depending on your material, okay, you would make various decisions. For example, if your material is glass fiber reinforced, melt flow rate can be a little tricky to interpret. So then typically you would use intrinsic viscosity, okay? If it's unfilled, melt flow rate's usually pretty good, okay? If you want to understand that full profile and make a comparison of A to B, then gel permeation chromatography is going to give you really the gold standard. It's all of that information is present. Again, different costs, different timings. You have to pick the right test for the application, okay? So what do we hope to get there? Well, again, principally what we're looking for is understanding whether this material's been degraded, perhaps during molding or during field service. But also help us to verify that the right resin grade was used, okay? Was Lexan 101 used or was Lexan 121 used? Again, melt flow rate can help us to identify that, okay? That's probably the only test of the ones we've talked about so far that would be useful for that. So we've talked about a variety of tests so far. I'm on timeout, don't worry. Okay. We've talked about a variety of tests, and Mike and I talked extensively about failure analysis. We would both get reports from, clients who had other labs maybe do some testing. We'd scratch our heads sometimes because they jumped in. The first test they did was NMR, nuclear magnetic resonance spectroscopy. Well, that's a great test. It's a fine test, but it's used in a very, very specific way. Why jump in with that? Or they would start with GCMS, gas chromatography, mass spectroscopy. Again, step through the right test. The core set of tests that I typically start with on a failure analysis are going to be fractography, FTIR, DSC, TGA, melt flow rate. Those are the 5 tests that I pretty much perform on most of my failure investigations. Once I get that data, now I'm going to determine, do I need to go deeper? Do I need to do some GCMS? Do I need to do some NMR? Do I need to do some specialty testing? What do I need? Okay? Again, I think it's premature to jump into some of those other tests. I can write certainly a laundry list of tests. That failure analysis is going to be very expensive and very time consuming. Keeping things practical. Fractography, FTIR, DSC, TGA, molecular weight determination. Great place to start for your failure analysis. Now, one test I'll add to that I've done more and more frequently now is going to be dynamic mechanical analysis. Now, that's a little tricky because I need kind of a set size. I need kind of a part or a region of the part that's about the neck down region of a tensile bar. But again, DMA is fantastic. And we have a talk later this morning from Mary Kozierzicki about DMA. And I highly encourage you to attend that. It's a thermal analysis technique like DSC, like TGA, except we're going to measure the viscoelastic nature of materials over that temperature range, or even over time, or over frequency. Very, very powerful technique, okay? I've been doing it more and more on failure investigations now, over, I would say, the last couple of years. So what we're going to look at, again, is principally, if we look at the blue curve, is going to be modulus as a function of temperature. If you knew Mike, this was a test that Mike was very passionate about. In fact, he practically took the plastics industry from here to here in terms of use of DMA, and that certainly has rubbed off on me. So, again, what you'll get in terms of a failure analysis here is you're going to understand the effects of temperature and time on the properties of materials, and we're going to be able to assess the inherent viscoelastic properties of our failed material. Again, that's extremely important, I think. So it's a test more and more that I've been doing. So, again, we went through that, I know, relatively quickly, but we have our microscopic examination, our material testing. We're going to then interpret our data. We're going to look at the entirety of that data, that jigsaw puzzle, right? All the pieces. We've got them all assembled now. We're going to identify our failure mechanism and our causal factors. Again, how and why the part failed. We're going to take that data, use it. Then we're going to prepare the report. A very, very key step in the failure analysis process, okay? Admittedly, maybe everybody's least favorite step in the process, because at this point, you've got your answer. And as I want to get on to the next project. I got more problems to solve. But this We talked about, we hope to learn something through that failure analysis process. And the way to do that is to get a report, to share that report, to get that knowledge distributed, okay? Because we're gonna see this same problem, I guarantee you, at some point. And if we have this report, okay, we can do that. So the report ought to include all the background information we collected. It ought to include all of those images, all of the, the images we took, all of the raw data. More importantly, it ought to include our interpretation of that. We saw this, that meant this to us, okay? We're gonna take that together, we're gonna include all of our conclusions, what did we draw, and hopefully there's some recommendations as to how we're gonna solve the problem, or what the next steps are. Do we need to do some more testing? Do we need to dive in? Do we need to do some kind of more formal root cause analysis thing? And again, oftentimes that provides the input for root cause analysis. Let's not, and I could spend some time here, but I'm not gonna. Let's not confuse failure analysis and root cause analysis. Root cause analysis goes an extra step. It dives in a little bit deeper than the failure analysis. Oftentimes the failure analysis is a great input for the RCA. When we look at these factors, okay, we talked about different mechanisms of plastic part failure, but these are our factors: materials, design, manufacturing, service conditions. All of the things that affect how our plastic part is going to perform come out of these 4 factors. Again, I like to put things in buckets. I compartmentalize things. Everything is going to fit into one of these 4 factors, and so that's what we're looking to identify. Again, conducted a survey, and I would say that this is pretty much right on the money, again, in my experience. By far, it seems like the leading factor that plays a role is going to be the material selection and the quality of the material. That seems like it's a big deal. Part design, the service conditions, and manufacturing, again, we don't want to ignore those. Those also contribute. All 4 of those are very, very important to look at as part of that failure analysis. That's our why. Our why comes out in one of these 4 categories, or, as I said before, multiple of these categories. Over the course of my experience, these are kind of the whys that keep coming up over and over again. And as an industry, we don't seem to learn. These are the problems, again, in my failure investigation history, that we keep making the mistakes, and we keep making it. Improper material selection. Molecular degradation during processing, during molding. Ignoring the consequences of time under load for plastics, which is very important. Excessively sharp corners in the part design. Not understanding the effects of strain rate, impact sensitivity, and chemical contact. Not understanding that. Again, we need to learn from our mistakes, or from others' mistakes, hopefully, so we can prevent our own. Kind of wrapping things up, or getting that direction anyway. I used to like to think that the failure analysis method was parallel to the scientific method. In fact, my wife's a teacher, and she was teaching 5th grade at the time, and she said, what you do with failure analysis is a lot like we do in our scientific method when we teach it to the kids. And I said, at first I thought, yeah, that's true. And then I said, no, that's not true. It's not true for a key reason. Failure analysis, we observe, we get our background information, we test, we interpret the data and conclusions. One key difference with the scientific method is that very early on, we hypothesize. We say, hey, this is what's going to happen. For example, if our very simplistic 5th grade science experiment, we think that if we water our lima beans with Coke instead of water, they'll get more energy and they'll grow faster. Well, that's our question. Then we test that, and then we see if it works, and if it doesn't, we kind of go back, okay? We re-question. If we do that with a failure analysis, hey, I think that this is environmental stress cracking. That's the wrong place to start. You can't get to that until the end. Because if you go into the investigation thinking, this is environmental stress cracking, I guarantee you will find supporting evidence because you're predetermined to think that. Again, with our failure analysis, we can't hypothesize early. We hypothesize, we come to the conclusions at the very end. So, and then just to end things, again, rules of a failure analysis: start and maintain an open mind. Again, that kind of goes back to that. You have to keep thinking about what, you got to keep an open mind, I should say. You can't form conclusions before or even during. Wait till you have all the data. The failure investigation has one objective: to determine the failure mechanism and the cause. okay? And you need to use that. The key to the failure analysis is not who I can blame. It's to find how and why the part failed. Allow the science to direct the investigation. We've talked about that. A closed mouth and just no foot. I tend now to be pretty, through the process of the failure analysis, I tend to be a little bit closed-lipped with my clients. Early on in my career, I would give them updates along the way. Hey, we saw this, we saw this, we saw this, I think it's this. Only to have contradictory data come up and have to kind of pull that back out. Meanwhile, the client said, oh, you said it was environmental stress cracking. So we went on and we started looking for chemicals, and they wasted a lot of time. So again, until you have all the data, maybe restrain yourself. Eating your own words is never palatable, especially when there's someone else's. Again, seek help, but form your own conclusions. Don't let anybody else sway you into thinking what the how and the why are. The simplest solution is often the best. Again, you can come up with elaborate solutions. Often the simplest is the most direct. The theory, however elegant, must agree with all our data. If we come to a conclusion, but we have contradictory data, we have to reconcile that, okay? Major incidents are often triggered by minor events. Again, we're looking for those minor events along the way. This is true. Having the wrong solution is, not frequently, but just is much worse than having no solution. If we come to the wrong conclusion and we publicize that and we go in a direction, we spend a lot of money and effort to fix that problem, and that wasn't the real problem, we've done an injustice, okay? Again, sometimes, it doesn't happen a lot, 2 or 3% of the time I do a failure analysis, I come to the end and I say, I don't know. And that's okay. It has to be okay. You can say, hopefully, I've ruled out this, I've ruled out this, I've ruled out this. Let's do some brainstorming again. Let's figure out what we think it could be at this point, okay? Wrapping things up, this is something that Mike said all the time. Mike loved to quote Michael Jordan. He did. He was a huge Bulls fan. And he would say this all the time. Fundamentals don't change. As an industry, as people, we need to understand the fundamentals of plastic. And that's what I'd encourage you to do. Now, before I let you out of here, I'm going to take a little survey right here. Okay. Who here, and just keep your hands raised through this, who here has been a client of Mike? Has hired Mike to solve a problem? I have. Who here has taken one of Mike's courses? Could be an AIM course, could be a one-day course, could be, a 2-hour lecture. Who here has taken one of Mike's courses? Who here has read one of Mike's articles? Can be an Antec paper, can be his stuff in injection molding or plastics technology magazine, one of the things that he's published. Okay, I include that. All Mike would ask for you who've raised your hands is that you pass that knowledge along to someone else. Mike was a huge believer that knowledge isn't power. Sharing knowledge is power. Thank you.
We have time for a couple of questions for Jeff.
Yes.
To make your analysis work, do you find fiberglass helpful, or is that just a whole new level of noise?
Yeah, the fiber reinforcement, certainly it changes the mechanical properties of the material. It makes fractography a lot more difficult. But, it's not noise, it adds a level of complexity to the failure analysis, yes. Glass fiber reinforced material is definitely more complex doing the failure analysis. Thank you.
Okay, thank you. Oh, got a question?
Oh,
I have a question.
yes.
What if we wouldn't observe any failure during the test? And would we redesign the specimen, or we make the intentional fall to the loading or environmental condition?
Okay.
So what if we just run all these tests, but we wouldn't observe the failure as we define it?
Okay, so then you're trying to recreate the failure, is what you're saying.
Yeah.
Yeah. That means that, have you done the failure analysis to identify how and why it failed? Because
if we do, and we won't see the point that our specimen really failed.
right, but
What should be the outcome?
if you have a failure, you have a field failure, right? You want to do the failure analysis. That will help you determine what tests to do to recreate the failure. Without the failure analysis, you're kind of shooting in the dark as to what tests to do to recreate it. So the failure analysis forms that that basis which you take the next step.
So we will continue further and further until we get the.
Well, the fructography, the analytical testing, all of that will tell you how it failed and why it failed. Then you can do the recreation. Then you can put it in the UV chamber. Then you can do fatigue testing on your part, whatever it is that you need to do. Yep. Yes.
About that binder, are there any plans to publish all his works in one spot?
Yeah, I wish there could be, but unfortunately, again, you know, the rights are owned by, well, what was Injection Molding Magazine, so I'm not sure where that goes, and now Plastics Technology. The good news is that you can find most of these online, especially the Plastics Technology ones.
Just to point to that though, so Plastic Technologists, I just learned this last week, they don't have some of the older articles because they were published on a different website.
Okay.
originally. So images have been lost in
Yeah.
transitions.
Unfortunately.
So you find older ones, they just don't have the images anymore.
Yeah. Yeah, that's,
So finding that kind of stuff is helpful.
Yeah.
And I've found some other ones that I haven't lost.
so, yep. I think, yep, we gotta go. You're up, Al?
I am, yes.
I will read this for you.
Okay, good. Thank you.
Al McGovern retired in July of 2021 after 43 years and 11 issued patents in the product and part design field as a mechanical engineer, director, and servant leader. His expertise encompasses numerous materials and manufacturing processes, domestic and international engineering and manufacturing, and use of additive manufacturing for design and production in that since 1991. He is passionate about his family, giving back to those in need and offering his expertise to smooth out the journey for future product and future product and part designers and engineers. His BSME is from Columbia University. You share that with Mike. That's where Mike went, Columbia.
Yeah.
And his MS, his master's degree, is from the University of Bridgeport in Connecticut. Al McGovern. And by the way, before Al gets up here, a huge thank you to Al. Al was the framework for all of this. He contacted all of our speakers. He kept things running. Al did a great job.
Thank you. Hey, everybody. So I have a cold, if you haven't figured out. Hopefully I won't sneeze or drool on my own computer here. So I knew Mike probably a little bit less time than Jeff. When I came to Chicago in '97, shortly after that, I got to run across Mike. I don't have a binder quite like that. I do have several of Mike's articles. It's how I first became aware of Mike. Now that I'm retired, they're probably in a box in the basement somewhere, and I couldn't tell you where. But Mike was great, and I enjoyed getting to know Mike a lot. We did have a lot of time together. Whenever I'd come to a conference like this, I always took Mike to dinner, bought him a drink. Last year for Glenn's thing, he came in the night before. Mike wore shorts. I don't know why he wore shorts all the time, but he had shorts at the bar at the St. Louis. So he was sitting there already when I came, and I bought him his drink, and he didn't want any of my ice cream. But so we knew each other well. He's from Long Island, born in Long Island, raised in Darien, Connecticut. My wife's from Stanford, I'm from Bridgeport, so we shared a lot. As Jeff said, we both attended Columbia. Mike said he didn't graduate. I don't know if that's true or not. He's 4 years older than I am, so he was there shortly after the campus had been taken over. So a lot to talk about, Mike and I. We never did get to see he and Audrey at the Grand Canyon. That was one of the things we were planning to do. Plans changed. So I'm going to talk a little bit about what Jeff just did, only from my perspective. I'm a product and part designer. All that alphabet soup, I don't want to know about it, okay? I don't want to understand it the way Jeff does, because I don't have time for that. There's a lot of other factors that go into making a product that I'm responsible for as the head of mechanical engineering. So I want to know that somebody's looking at it, but it isn't going to be this guy. And I don't necessarily want my engineers spending their time doing that, but I want them to know somebody that I can trust. Mike was that guy, always that guy. I knew the Madison group for a long time. I actually worked in Madison for a year. And so I knew of them well. I think highly of them, very highly of them. But Mike was my guy. That's just how it was. I had Mike on my phone. I could call Mike at any time. He would take my call and answer any question I had. And if it required a little deeper dive, then he'd send me a quote, and we'd go on from there. But I always found that Mike could talk to an idiot like me and make it clear so that I could then explain what happened to people above me who are wondering, WTF, Al, what happened here? Why is this part broken? Why did this not work? You know, you're supposed to be the guy. So he could make that clear. And we also use Mike a lot for heads up before we got deep into the design. I believe a lot in simulation. I believe a lot in upfront work. You're going to pay me now or pay me later, and if you're old enough to remember that I think Mobil Oil commercial, whatever it was, you're going to pay me now or pay me later. So I'd rather pay up front, saves a lot of money down the road, and a lot of embarrassment, quite frankly. To my credit, I can say I have no boat anchors in my history of plastic parts. If you're familiar with a boat anchor, that's a mold that you built and then didn't work. So what is it good for? A boat anchor. So I have none of those in my history, and Mike is a part of that as well. Okay, so let me explain a little bit about that. He was an extraordinary materials analyst, but there were other good people. You just heard one right now, if you were here for Jeff's talk, and you'll hear others if you stay. So not the only one, right? But he's the guy I always went to when a problem arose, and he had that special ability that anyone, really everyone, could understand and act upon without making you feel inferior or ignorant, even when I was probably both. So what was so special? He prepared a very detailed report as part of his deliverables, typically in two parts. The first part had all the graphs, all that stuff you just saw Jeff talk about, all that alphabet soup stuff. It was all in there. Mike had it all, as does Jeff, of course. But he separated that because he knew I didn't want to see it. I want to know what's wrong or what, tell me what I need to know. That was his executive summary. That was usually all words. It never had a graph. It might have a table, but it never had a graph. I don't know that Mike did that only for me. Maybe I was his idiot client. I don't know that. But he did it, and it was very helpful for me to explain what's going on. And then he'd get on a call. This is important, whether it was a conference call, video call afterwards. COVID, of course, we did more video calls. Mike was in Sedona when a time I came to shore. In the early days, of course, he was up in Wisconsin. I was in Chicago, so we could meet. But when he went out to Sedona, he and Audrey said, enough on the cold, we're going to Sedona. We would talk on the phone or by video and review the report. So that I found that to be special. Now, I'm not saying he was Superman, okay? Look at those pictures. So he wasn't. Maybe he was more like Mr. Rogers, right? And apologies for the poor editing of his face. I'm not the editor in my family. So how about some examples? Let's talk about this. So I have a few examples. I have all the parts here that I'm going to show you. They're small parts, and by the time I show you one, I'm going to be on to the next one. So I think we're going to find it. It's not practical to do that. But let me encourage you afterwards to come and see what I have here, okay? If you're interested, of course. You can come even if you're not interested. I'll still talk. So thanks to the folks at Shore for letting me do this. I retired there 3.5 years ago, so I had to get permission to show these, and they were great. Appreciate that. Those showcase his special skills. So with that said, it's a beautiful day in the neighborhood. Let's get going. So first one, small, very small part. I'll hold it up for you. You could see, you'll see in the next slide, I have it in a dime. These are the little parts here. They're little bugger parts. They go on a lavalier microphone that would be worn here, or as you can see in the theater, okay, the lower picture there, you can see they're stitching that right into the actor's hair. It goes into costumes, so you don't see it, but it's there. It slipped on the end of the lav to make the microphone perform a little differently in the way it picked up the speech. It had to be easy to install and remove, but it had to stay on there while the performers were running around the stage. Early versions were cracking. And so we knew this might happen. This wasn't entirely a surprise. The parts are so small. Even when we were just working with prototypes, we had a hard time getting them so that they would stay on the mic, but not come off and grip them. We nano-coated them so that perspiration rolled off and didn't work its way down into the microphone. So we knew this was a potential problem, and it did come up. So we shined the bat light in the sky, and we got Mike on the horn. You're going to see this dime in all of my photographs that I took at home here. I was hard pressed to find change in my house. Since COVID, I don't have any cash or change, but I found a dime. So you'll see this dime everywhere, but it gives you a relative scale, just how tiny that part is. The lower part shows those little ribs, crushed ribs, we put in to try and make sure it stayed on, but didn't come off unnecessarily. So this was a 61-page report, one of the longest and largest Mike ever did for me. It had all those things Jeff said. All those initials were in there, every one. But again, his summary is what I was after. So this is an eye chart, I think, right? Cover one eye, maybe a little easier to read. So he looked at the raw material for us and had parts. The parts were what we said, materials, what it should have been. These were molded by AccuMold in Iowa. If you have to work with AccuMold, any of you know, top shelf company, top notch. So wasn't worried about that at all. But we had to be confirmed. The cracks, exactly what Jeff said. Be careful how you handle these parts. They would come back cracked, and we'd all look at that, it's cracked, and we'd squeeze it again and break it again. So idiots that we were. We finally did get some good parts to Mike, and he was able to do his thing. He showed where the cracks occurred, where the weld line was. He took some great pictures of that. There's a point at which, as you get higher in magnification, it goes farther over my head. I just can't understand all the little things in there. I just don't. I appreciate that Mike does. So that's why, again, you're talking to me. So, and then he took parts and actually forced a crack in them. So we were able to make a few changes in this part. We kind of knew what was happening. Just tweak the gate location just a little bit so that the knit line came up one of these inner walls versus in line with the slot. Just that tiny little tweak. Mike helped us confirm that. We didn't know exactly where the knit line was going to be in this part, despite doing mold filling simulation. It's a Mike molded part, so it's not always as accurate as you'd like it to be. So, great job for Mike. That helped us a great deal. Next part is something in the Axient Digital product family. The top and bottom housings for this body pack. It's worn here on the side. This one happens to be used for in-ear monitors, so it's receiver. Some are used for a lavalier mic and it transmits. Same pack, just different antenna configurations. Screwed together, had to be very, very tight fit. It's very densely packaged. Excuse me. Had to be RF transparent, so plastic was the material. The battery door is not, but the rest of it is RF transparent nylon. Cycle, excuse me. There's a gasket seal interface all around here. You'll see in the next pictures. That was critical for the IP rating we were after for this product. Again, these are sewn into costumes as well to go with that lavalier mic that I just showed you. So we wanted to make sure, I have to say sure and certain, right? These are sure products. We wanted to be certain that this product would last 20, 30, 40 years. Sure products last forever. That's just the history of the company. In fact, April 25th will be 100 years the company has been in existence in Chicago. And there are microphones from 1935 that people still use today. So in movies, sometimes in actual movies, they come and get our mics. So they gotta work. And this is a wireless system. We'll see, wireless is new, relatively new. So but we want it to last forever. Those are plastic parts. We tightly put together. They're going to be under compression with a gasket. Is it going to stay? So we had to get data from Mike that nobody had, right? This kind of data for long term isn't in a data sheet. So we hired Mike to get this data for us. So he decided to focus on creep at high temp and the service hours. And then we also wanted more data to help us do finite element analysis, drop test. All Sure products have to withstand drop from certain heights. Microphones from 6 feet, body packs from 40 inches. So these had to work. So here's the parts. I won't take any, again, I have them. I'll be happy to go through them with you. There's the die, plastic parts you can see. You'll see some inserts. We insert mold, brass inserts to control the compression of the gasket. If you ever use gaskets in a part, you don't just tighten the screw till you feel it's tight. You gotta have a positive stop, or you don't have a gasket seal, or you won't have it for long. So these are all insert molded in there. So there's a lot going on in this part, as you can see, both of these parts. This one was a little simpler, 20 pages for graphs, and then his 5-page summary, which we can just take kind of right here. We asked him to evaluate 3 materials. I think I saw it in the previous slide, just saw that. We weren't sure which one we were going to use. We wanted to use cycloid because we use cycloid lots of places. These parts are molded in Taiwan. So we want that molder has this material, we know we can trust it, it's black. Sure, things are all black. Our microphones are primarily black, so you don't really see them. That's the whole idea, you don't want to see it, you just want to hear from it. So he did a test, and the cycloid would fail first, but this 19.7 years, we'll live with that. That'll work. And again, it's a worst case in simulation, so, or analysis, I guess. So that told us what we needed to know. And then he gave us the working stress on all the materials, so we could drive this into, and actually these Excel files just got loaded right into the Abacus FEA tool that we had. So we knew what we were up against right away. Again, the confidence that gave us the product wasn't on the market yet, so we were making decisions that would have great impact quickly. This was a highly anticipated product, for sure. And this was his figure 20, the last graph in his report. And the black here is the cycloid, as you can see, and the red is the cycloid, different temps. So they're grouped like this. This is the 23C, and these are the 63C. And you can just see the working stress. It's a little higher than, lower on some, but we were okay with these materials. It gave us the confidence that cycloid would do what we needed to do in the space we had. Okay, third example. Gooseneck. This is a gooseneck. This one is an older style, does not have the part I'm going to show you here in a minute. There's an isolation, a rubber shock mount, isolation mount here. This was, it's meant to keep this kind of thing from working its way up to the microphone and you hear it. These are made by a company in Taiwan who outsources the rubber part. Failed part were used in Wyoming. This is an actual picture of the Wyoming chamber. You can find anything on the internet now. Right there is a little rubber mount. And so we asked Mike, these parts were cracking. Tell us, what's the origin, and confirm the rubber compound. We didn't think we would have a problem with the compound. So a 56-page report, and here I'll just step you through this. So here's the gooseneck. Okay, flexible up there, flexible down here, solid in the middle. There's the rubber part, a little close-up of the rubber part. These are the two parts themselves with my ubiquitous die. So what did Mike find out for us? This was a surprise to us. The failure mode was in where there's a sharp corner. These parts were in production before I started at Shure. I got to know Mike because when I came to Chicago, I was hired to fix the parts of plastic, the problems with plastic parts in what was otherwise a metal company, telephone products metal company. And when I saw what they were doing, it was pretty easy stuff to fix. I thought, well, that probably can't be too prevalent, right? And you'd be amazed at how many parts have sharp corners in them, plastic parts. I'm always amazed at that. It just floors me every time. And that's what was happening. There's sharp corners in there. I don't know if the guy in Wyoming was angry that day. He's beating it to death, but it cracked. But we also found that it was not the rubber we wanted on the drawing. So Mike goes into detail about that here, that they're produced from nitro. We wanted butyl. He also found it had filler in it. And then down here he found it didn't have the full zinc oxide, so the catalyst wasn't there either. Otherwise it was the exact part of the drawing. So we went back to the vendor, said, hey, take a look at this. Oh yeah, we went to this vendor. Oh, we're so sorry. We gave you the wrong material. It won't happen again. So a couple of years went by, and we're having the problem again. I'm only telling you that because that's how the guys at Sure found out Mike had passed. They reached back out to Mike just recently, said, hey, Mike, can you help us? Finally, Audrey reached back out and said, hey, Mike's passed. So when I found that out, he said, go to the Madison group, they'll help you. I couldn't do that before. Jeff and I had this conversation. Mike was my guy, so that's how it went. So Mike was very helpful here. We did not expect that at all. That was a kicker that we did not understand at all. Once the parts came, the right material, of course, then it worked fine. Right? Just great. And when I say worked fine, obviously we did a lot of testing to make sure that it would hold up. So the KSM-8 cartridge housing. We do have this microphone here. This is brand new technology to the microphone industry, actually. And one I'm especially proud of because my time at Branson Ultrasonics gave me the belief that they could do anything. And I just saw it with my own eyes everywhere I've gone. So, but I didn't do much with laser welding. So these parts here, there's a laser weld in here, right in here. This upper cavity and this lower cavity, there's air channels in here, 4 channels of air, and they need to be airtight. There's something happening acoustically up here and something differently happening down here, and it's that interaction that gives this microphone its unique ability for sound. It's James Taylor happens to like that mic a lot. So the parts are molded in Taiwan. I'm molded for sure for 25 years, so good company, very good company. There's a small metal disc in one of the parts that's ultrasonically welded first. Then the parts are brought together. There's 4 trapezoidal shaped joints, meaning there's 16 mating surfaces. The laser welder comes from the inside. Branson never did that before, but I knew Hugh McNair and Paul Rooney called these guys up and said, hey, up in Honeywell Falls, here's what we have, what can we do? And they developed this process for us, which they use in other places now. They laser weld from the inside. But the laser welds, you got to pass the energy, the laser light through a material, and then it has to get and stop with the other material. So a natural color is where the light goes through, and the black color is where it stops. So on all those 4 surfaces, it heats up, there's pressure applied, the joint is formed. And it's airtight, we check the airtight seal after. So Mike confirmed that composition for us. We were asked him to do that. So again, here's the parts. There's a little metal part ultrasonically welded in. Here's your little trapezoidal shapes. These were tweaked up to 1/1000th of an inch, believe it or not. And the molder in Taiwan did a great job adjusting these. Again, you see the dimes, you get a sense of the size. So this was an easy one for Mike, okay? Very small, you saw a very small report. 7-page. He did this one at lunchtime. He confirmed the material. This was really important because we had to know what we were laser welding. That laser process was very, very sensitive. The laser mirrors and such were $100,000 each. Each system we had two was a backup. So we didn't want to fool around with that. So again, Mike made it very clear. This was an easy one for him, right? This is just telling us it's the material what we want it to be, and it was. We were worried they might put a black filler in there or something else. We wanted to know exactly what we had. And then this is a microphone internal frame. So I'll show you the next picture, next slide. Inside here is a frame. It's made from DuPont Zytel, a 9166, black material. It's a structural element. A lot of things happening. The way the microphone attaches up here, the way the antenna and the charging contacts attach down here. There's a lot going on. Again, next slide, I'll show you a little more about that. Dimensional stability, it's nylon, so it had to be manufactured properly. Mike gave us counsel on what to tell the molder after you mold it, certainly dry, how to dry it, but also after you're done with it, it's in Taiwan. Parts coming out of Taiwan in June, July, August are going to be a little more moist. So they got to be dried and packaged because they're going to get on a boat and come all the way across the water and soak up more water. We can't have that, so they had to be dried carefully. I don't mention that here, but Mike gave us that counsel as well. It's written onto the drawing. So we asked him to confirm the resin. What was on the drawing. This was, again, a simpler one for Mike. So here you can see the part, the little diamonds. This is the biggest part of the ones we looked at today. Batteries in here. This product uses a rechargeable lithium cell, but for some of our lower end products, we make it so you can drop in alkaline batteries. The high end products are used, as you may have noticed here, there's guys running around making sure all the microphones work. So they're paying people to see that everything's right. Sometimes it goes to a church or a meeting hall or something, and they haven't remembered to put the thing back in the charging cradle after they used it. I see this in my own retirement center where we have shirt gear. They don't always remember to plug it back in the charging cradle. So when you need to use it and it doesn't work, you could pull out the rechargeable battery and put in at least alkalines. Almost everybody has alkaline AA's. Anyway, that's what it is. So lots going on here. All these points are tied to other mating features in the other parts. So Mike confirmed that for us. It was, he looked at a few things here and told us about the carrier for the black colorant and what we had, which was good. He also tested another material. It had an LDPE carrier in the black resin. We saw this a lot, where not everybody uses the right carrier for the colorant. So they just select, I'm Mercedes, she's the coloring girl over there. Something I didn't understand. That is an acronym I do get, LDPE, so I'm not an idiot, but I play one on TV, I guess. So there we go. So look, DSC, Jeff, and there were DMA and some of these other things as well. Mike was big on average molecular weight studies. That was a big thing for him. So he told us exactly what we need to know, and we made sure, therefore, that what we specified to the molder, this is what you got to use. Don't go buy a natural and throw somebody else's colorant in there, because it would not work. It would give us different performance. So Mike helped us to see that. So I think that's it. I had to put this in here. Mike signed every report that way. A little sloppy, I think, but well, it's his signature. So I'm happy to take any questions. And I do have the parts here as well. Okay, I think we're 9:29. So there's a coffee break. right, 9:30. If you're a speaker, please stay here. Pedro's going to take a picture of you, of us. And we're going to send that to Audrey.
Nice job, Al.
Thank you. You too.